This video introduces the topic of finding real and complex zeros as well as graphing polynomials. The learning outcomes are to use definitions of zeros, turning points, and end behavior to describe polynomial graphs. To find all real and complex roots of a polynomial by using the conjugate zeros theorem, the fundamental theorem of algebra, and the intermediate theorem, as well as the previously covered theorems. And finally, to use this information to graph polynomials. First, let's take a look at a graph to visually see the definitions of zeros and turning points. Here we see a polynomial graph, and where the graph touches or passes through the x-axis are the zeros, since when we plug in these x values into our polynomial function, the y value is 0. So we can use the label of zeros and x-intercepts interchangeably. Remember, we can find these x-intercepts, or zeros, by setting the factors of the polynomial equal to 0. So for this graph, we can see that x plus 3, or x minus a negative 3, is a factor, and we see that there is another factor at x minus 4. Since we see that the graph curves through the x value of 4. In fact, we will discuss more about what is happening at x is equal to 4 of this graph later in this video. Turning points are points where the graph changes from increasing to decreasing or from decreasing to increasing intervals. We can see from the graph that the y values are decreasing as we move from left to right on the graph. So we have a decreasing interval from negative infinity to about negative 2.25. Remember that the interval negative infinity to negative 2.25 is describing the x values, while the word decreasing is describing the y values of the graph. Then, from negative 2.25 to about 0, we see that the y values are increasing. So we have found that there is a turning point at the x value of negative 2.25 and the y value of about a negative 1,000. Again, we see a change from increasing to decreasing at the x value of 0. So there is a turning point at x is equal to 0 and y is equal to a negative 100. There is another change from decreasing to increasing when x is about 1.5. So here is another turning point at 1.5 comma negative 200. Therefore, we can say that we will find at least one turning point between two consecutive zeros. In fact, for this graph, we found 3 turning points, and we will explain this phenomenon later in the video. One last thing I want to mention about this graph is the end behavior of this graph. To describe the end behavior, we first talk about the x values to see which end of the graph we want to describe. When we say, as x approaches negative infinity, this means we need to look at the far left of the graph and ask, what are the y values doing? Looking at the graph at the far left, we see that the y values on the graph are approaching positive infinity. So we write this as x approaches negative infinity, y approaches positive infinity. Now let's take a look on the right side of the graph as x approaches positive infinity, and we ask, what are the y values doing? From the graph, we see that as x approaches positive infinity, the y values are approaching positive infinity. To practice end behavior, let's return to our parent functions and the handout where we graphed the parent functions. You may want to pause this video here and try your hand at writing end behavior for each of the parent graphs before I continue to do the same here. So let's go over the end behaviors of our parent function. So notice, as we're looking over here towards negative infinity, we're going to see that our y value still continues to be at 3. So we're going to write that as x goes to negative infinity, our y value goes to 3. So it stays the same. We can do the same thing as x goes to positive infinity. That means we're looking over here at x is equal to positive infinity. We see that our y values are still staying at 3. When we go to linear, as I go over here towards negative infinity, we see that our y values will keep going downward. So we find that as x goes to negative infinity, our y value also goes to negative infinity. When we're looking over here at x is equal to a positive infinity, our y values are going upward. So we find that as x goes to positive infinity, our y values go to positive infinity. Going to absolute value, as x goes to negative infinity, we're going to see that our y values are getting bigger and bigger, and they will approach positive infinity. So for absolute value, as x goes to negative infinity, we found that our y values go to positive infinity. Likewise, when we go to the right, we're going to positive infinity for the x's, and my y values are constantly going upward. So as x goes to positive infinity, y is going to also positive infinity. If we take a look at quadratic, what we find is that as x goes to infinity, our y values are going upward to positive infinity. So we're going to write down that as x goes to infinity, our y value goes to positive infinity. And if we go to, sorry, that was negative. If we go to the right, where x is going to a positive infinity, we see our y value also going to a positive infinity. So I'm just going to write it over here. As x goes to positive infinity, our y value also goes to positive infinity. Over here for our square root, notice we cannot go to negative infinity. However, we can go towards 0. So we would say that as x goes towards 0, our y values are also going towards 0. So notice our y values were up here, and as we're getting closer, as x goes closer to 0, the y values are getting closer to 0. But we can say as x goes to infinity that our y value is also going to infinity, as we can see them going upward here. And last but not least, on this page, we see that as x goes to negative infinity, that our y values will be going to negative infinity as well. And as x goes to a positive infinity, we see that our y values are also going to a positive infinity. As x goes to a positive number, y values are also going to a positive number. Now, one thing I do want you to notice is that our end behaviors are dependent on our domain and range. So if we look at our domain, we see how it's going from negative infinity to positive infinity, and we see the same thing here. If we come down to our square root, notice that our domain here is from 0 to infinity, so our x's over here are also going from 0 to infinity. So our end behavior is also dependent on our domain. Let's continue. For cube root, we can see as x goes to negative infinity, our y values are going lower and lower and lower. Hard to tell in this graph, but what we find is that as x goes to negative infinity, our y values are also going to negative infinity. And if we go to the right, we can see that as x goes to positive infinity, our y values are also increasing. So as x goes to infinity, our y values go to infinity. For reciprocal, we see as x goes to infinity this way, negative infinity, our y values are getting closer and closer to 0. So we're going to find that x goes to negative infinity, our y values are getting closer to 0. In fact, we put a little 0 with a little negative sign to show you that they're coming from below the graph. If we go to the right side, as x goes to positive infinity, our y values are getting closer to 0 as well. We find our y values are getting closer to 0, but we would say a little plus sign because they're positive numbers. The little plus and minus stuff you don't really need to know, but you do need to know what happens in terms of our graphs and our end behaviors. So let's take a look at this one over here. We can see as x goes to negative infinity, our y value, I'm going to write it right here. As x goes to negative infinity, our y values are going to 0, and they're going from above. And as x goes to positive infinity, our y values are going to 0 also from above. So we can see that right here. Finally, we can go to these last few and we see that we can say that as x goes to 0, again, that remember our domain, we can see that our y values are going down, 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 so our y values are going to negative infinity. As we go to the right, as x goes to positive infinity, we can see our y values are going to go upward ever so slightly, but they will go to positive infinity. So again, remember, our x's are dependent on our domain, and our y values are dependent on our range. If we look at our exponential here, as x goes to negative infinity, we see that our y values are getting closer to 0, and again we can say from above. And as x goes to positive infinity, we see our y values increasing forever, so we see that going up that way. Now, for the sine graph, which is this last one that we have right here, things are a little bit different, because what happens over here at negative infinity is that this graph keeps doing this, going up and down. So we really don't have end behaviors for sine graph or cosine graph. So same thing here, it'll go up and down, and so we will never have our end behavior like we did for the other ones.